In this section, we are going to talk about, we're going to continue talking about measuring pH. We're going to talk about the pH scale. We're going to talk about what neutral pH means, and we're going to talk about why pure water has a neutral pH. So as far as measuring pH is concerned, again, this is a little bit of a recap of what we talked about in the previous sections, although this first point might be a little bit new. For most aqueous solutions, aqueous basically means for most water-based solutions that you have an acid or a base dissolved in, the pH can be anywhere from 0 to 14. It doesn't have to be stuck between those 2 points. It can actually be less than 0 and it can be more than 14. But for most aqueous solutions, for most water-based solutions, it's almost always between 0 and 14. If you have a pH of 0, again, if you remember what I said in the previous section, the lower the number is, the more acidic it is. So a liquid that has a pH of 0 means that the acid concentration is very high, or you can say that the liquid is very acidic. And again, this can be a little bit confusing because the lower the number, the more acidic it is. But there you have it. And if you have a liquid with a pH of 14, which is on the other end of the spectrum, then you would say that that liquid is very basic, or the concentration of base in that liquid is very high, and the concentration of acid in this liquid is very low. Halfway in between 0 and 14, we have the number 7. If you have a liquid where the pH is 7, you say that the liquid is neutral as far as pH is concerned. What that means is that at pH 7, your liquid has equal amounts of acid and equal amounts of base dissolved in them, and that's halfway between 0 and 14. So that's neutral pH. At this point, I want to talk about pure water. Some of you may know that pure water, just straight water, the pH of pure water is pH 7, which means it has a neutral pH. It has equal amounts of acid and equal amounts of base. In this slide, I basically want to describe why that's the case. So imagine that you have a container of just pure water molecules, so just liquid water in a container. And most of those water molecules are not doing anything. However, let's imagine that there are 2 water molecules that are going to do something, shown in this equation here. Let's pretend that this water molecule on the left is going to donate one of its H pluses to the water molecule on the right. Because the water molecule on the left is donating an H plus, you can think of this water molecule as an acid. Because of this water molecule, this one on the right is accepting an H plus, you can think of it as a base. So every once in a while in your sea of water molecules, you'll have one that acts as an acid, and because it's acting as an acid, you have to have another one that is acting as a base. And because of that, this water molecule, since it's accepting an H plus, is going to be turned into the H3O plus that's shown here on the right side of the arrow. And because this one is doing the donating, it is going to turn into OH minus. And as I mentioned previously, you can think of H3O plus as sort of being a surrogate for acid. And you can also think of OH minus as basically being a surrogate for base. So even though most of the water molecules in your pure container of water are doing nothing, every once in a while one of them will donate to another one of them. And because they have to do this in pairs, one donates, one accepts, you will always make basically one acid molecule and one base molecule. And as I said, neutral pH means that you have equal amounts of acid and equal amounts of base. And hopefully you can see that in this equation. Whenever you have one water molecule donate an H plus to the other, you will always make basically one acid. If you want to think of it as being an acid molecule, make one acid molecule, and you will also make one base molecule, and you will have equal amounts of each. And because you have equal amounts of each, there will be equal amounts of acid and base, which means you will have a neutral pH. So purified water at the correct temperature, basically at room temperature, has a pH of approximately 7, which means neutral pH. And if you want to think about it this way, even though it's a little bit weird, this water molecule over here is the acid. It turns into a conjugate base. This water molecule over here was a base, and it is turned into a conjugate acid when it accepts an H plus ion. And then again, just to give you a punchline, pure water is actually both a weak acid and a weak base at the same time. And because it is both of them, the pH of pure water is 7. In other words, the pure water has a neutral pH. And so if you could zoom in and look at the atoms and molecules in a container of pure water, what you would see is that almost all of the water molecules still behave like water molecules, but every once in a while one water molecule will donate to another water molecule and you will get equal amounts of H3O plus and equal amounts of OH minus. So because you have equal amounts of acid and base, you basically have a neutral liquid. So pure water has pH of 7. It's neutral pH. Let's see. This is just a summary of what I said in the previous slide. So because it has an equal number of H3O plus and O minus, it's not acidic, it's not basic, it's neutral as far as acidity and basicity are concerned. Okay, so this some of you probably have seen before. This is traditionally called a pH scale. Basically, what I'm trying to show you is that for most aqueous liquids, for most water-based liquids, the pH, depending on what the liquid is, depending on how much acid and how much base are dissolved in the liquid, the pH can range anywhere from about pH 0 to about pH 14. And in the middle is pH 7, which is neutral pH. Anything to the left here is acidic pH. Anything to the right here is basic pH. So there's neutral. And the idea is that as you travel toward lower and lower numbers, the concentration or the amount of H3O plus in your liquid increases, which means that your solution becomes more acidic and the pH becomes lower and lower and lower. And the amount of OH minus in your liquid actually gets smaller and smaller and smaller. As you travel in the opposite direction, as the pH numbers get bigger, the amount of H3O plus in your liquid gets lower and lower and lower. The concentration becomes lower. What you say is that your liquid becomes more and more basic as you travel in the right direction, and the amount of OH minus in your liquid increases as you travel toward the right. So here's neutral pH. As you travel in this direction, your liquid becomes more acidic. As you travel in this direction, in other words, if the pH increases, your solution becomes more basic. And just to give you a couple of signposts, pure water has a pH of 7. 0.1 molar hydrochloric acid has a pH of 1. The reason that it has a pH of 1 comes from the formula for pH. If you take the logarithm of 0.1 molar, the logarithm is -1. However, the formula for pH is -1 times the logarithm, so -1 times -1 is +1. So that's why the pH of 0.1 molar HCl is +1. Stomach acid, the acid in your stomach, is somewhere between about pH 1 and 2, so it's pretty acidic. Blood has a slightly basic pH. I think it's around 7.3. It can fluctuate a little bit, but not very much. So the pH of your blood is generally around here. 0.1 molar sodium hydroxide is the pH is about 13, so it's very basic. So that's basically the pH scale. Again, just to emphasize, these numbers here on this line represent different pHs. So if you had a liquid and the pH was 1, what you would say is that it is relatively acidic compared to other liquids that have pHs higher than that. And if you had a liquid with pH 0, it would be very acidic. It would be more acidic than any other liquid with a pH higher than that. If you had a liquid of pH 7, it's basically neutral. It's not acidic and it's not basic. And if you have liquids with pHs higher than 7, then what you say is those liquids have a basic pH. And the more you travel in this direction off to the right, the more basic those solutions are. So again, just to summarize, and this is sort of a list of what I expect you to be able to do. If I give you the pH of some liquid, you should be able to tell me if it's acidic, basic, or neutral. So if the pH is less than 7, you'd say it's acidic. If it's bigger than 7, you'd say it's basic. And if it's exactly 7, you'd say it's neutral. If I give you the molar concentration of H3O plus in a solution, in a liquid, you should be able to give me the pH. Now, I would give you the formula for pH, -1 times the logarithm of the H3O plus concentration in units of molarity, but basically giving you this number, molar concentration of H3O plus, then you just have to plug it into the pH formula. And so this is going to require you probably to be able to enter numbers using scientific notation on your calculator. Also require you to be able to use the logarithm button on your calculator. And then finally, if I tell you, this bullet point is a more complicated version of bullet point number 2. In other words, if I tell you that you dissolve 10 to the -4 moles of hydrochloric acid in 0.1 liters of water, and that all of the H plus in the hydrochloric acid is donated to water molecules because HCl is a strong acid, you should be able to compute the molarity, and that would be just moles divided by liters. And again, I would give you the formulas. To do that, you'd just have to be able to use the formulas. And once you computed the molarity, then you should be able to tell me the pH by using the pH formula, again, which I would give to you. It's a multi-step problem, so it might be difficult for some of you, but that is a type of question that I could ask. So that's the end of sort of pH and acidity. It's not really the end. There's one other little section that I'd like to go over, but that's going to get its own small video.